Hello, I'm Tanishq Upasani and this is my partner Sahil Kadam. Today we are presenting ATMOS, a real-time weather data fusion platform that demonstrates distributed cloud computing at scale.
Okay, so moving on to the project goals, ATMOS tackles the challenge of aggregating weather data at scale. We collect real-time data from 50 major US cities, processing over 600 data points per hour. Our system provides instant access to current condition and historical trends through a REST API with response times under 100 milliseconds thanks to the intelligent caching. The platform demonstrates key distributed system concepts, including asynchronous processing, then data caching, and horizontal scalability.
Our architecture leverages four cloud technologies. First, Flask REST API serves as the communication layer, exposing endpoints for the weather queries. Second, the RabbitMQ with Celery handles distributed task scheduling. When we need to collect weather data, tasks are queued and processed by available workers, enabling horizontal scaling. Third, PostgreSQL provides reliable persistent storage, currently holding over 14,000 weather observations with time series optimized queries. Finally, Redis acts as our caching layer, storing frequently requested data in memory with a 5-minute TTL, achieving over 85% cache hit rates and reducing response times from seconds to milliseconds.
So let me walk through our architecture. At the very top, we have external weather API with weatherapi.com in our case. So our salary worker nodes poll these APIs every 5 minutes for 50 cities. Then RabbitMQ sits in the middle as our message broker, distributing like collection tasks across the available workers. This design is fault tolerant if a worker crashes and RabbitMQ resigns its task. Collected data flows into PostgreSQL, our primary data store. Before responding to user queries, we check Redis first, our in-memory cache. If the data exists and it isn't stale, we return it immediately. Cache misses query PostgreSQL, then populate Redis for subsequent requests. This cache aside pattern dramatically improves performance. Finally, our Flask API exposes the data via RESTful endpoints consumed by React dashboard that displays real-time weather condition, trends, system metrics. All components run in Docker containers for consistent deployment.
Let's examine how data flows through the system. The collection pipeline starts with the Celery beat, our scheduler, which triggers data collection every 5 minutes. Tasks are queued in RabbitMQ and picked up by available workers. Workers call the external API, validate the response, and store it in the PostgreSQL. For user queries, request hits our Flask API, which first checks Redis with an 85% cache hit rate. Most requests are served in under 50 milliseconds directly from the memory. Cache misses query PostgreSQL. This takes longer, around 200 milliseconds, but we immediately cache the result. This two-tier storage strategy balances speed with data freshness.
So moving on to the implementation stack, our software and hardware. Our implementation uses Python 3.11 as the primary language. Flask provides the REST API. Celery with RabbitMQ handles distributed tasks. PostgreSQL stores our data and Redis caches frequently accessed records. The front end is built with React for a modern responsive interface. Everything runs in Docker containers for portability. While we develop locally, the architecture is cloud ready. We can deploy to Google Cloud Platform using Compute Engine, VMs, Cloud SQL, and Memory Store, demonstrating true data center scale patterns.
The debugging and post testing. Testing was crucial for reliability. We implemented comprehensive unit tests covering individual components, API endpoints, return correct status codes, database connection work properly, and cache operations function as expected. Integration tests verify the entire pipeline. We make a request, ensure it's cached correctly, check the database was updated, and validate the response format. For load testing, we simulated 20 concurrent requests to verify the system handles real world traffic. We maintained the sub 200 millisecond average response times with a 95% success rate.
Okay, so moving on to the demo part, I'll just show. Okay, so here's our React dashboard showing real-time data for 50 cities. You can see current temperature, humidity, wind speed, and more. Notice the detailed weather cards with UV index and air quality. Okay, I'll just click on one, Los Angeles. So over here, selecting a city displays its 24-hour temperature trend. This data comes from PostgreSQL database. Next, I'll just show this. Okay, so this is our REST API requesting Boulder's weather return JSON data. Yeah, we can watch the response time. It changes. Next, here we have API exposes multiple endpoints. The statistics endpoint shows total cities, records, and collection rates, all variable programmatically. And next. Yeah, so this is our worker activity. In this terminal, we can see our salary workers actively collecting data. Each city collection takes like 2 to 3 seconds and worker process these tasks in parallel.
Let's talk about scalability. Currently, we handle 50 cities with 600 data points per hour. Our API comfortably serves 20 plus concurrent requests with sub 200 millisecond responses. The cache hit rate of 85% significantly reduces database load. We have identified three main bottlenecks. First, the external API limit rate. We are well under the 1 million monthly calls, but this would limit expansion beyond 200 cities. Second, PostGRE SQL instance could become a read bottleneck under heavy query load. Third, Redis is a single point of failure. To scale further, we'd add more Celery workers. This is trivial with our architecture. Just spin up more containers. For the database, we'd implement read replicas for query distribution. Redis could be clustered for high availability. Finally, we'd add a load balancer in front of multiple API instances. The beauty of our microservices architecture is that each component can scale independently.
So the lessons learned are like from this project, it taught us valuable lessons about distributed system. Caching provide like critical that 85% hit rate reduces our database load fivefold. Asynchronous processing with message queues means we can like scale horizontally without code changes. We face challenges with API rate limits and finding the right balance between data freshness and cache efficiency. Also, debugging a distributed system is harder than monolithic apps. Issues can occur in any component. These patterns apply broadly on IoT platforms, real-time analytics, and monitoring system all use similar architectures. The skills we developed here directly transfer to building production-scale cloud applications.
To summarize, ATMOS demonstrates data center scale computing principles through real-world weather data aggregation.
We successfully integrated 4 cloud technologies, achieving sub 200 millisecond response times while processing 600 data points per hour. The architecture is production ready and horizontally scalable.
Thank you for watching. Have a good day.